Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at velocity vectors. We'll start with this question. I walk 2 kilometers an hour north. My friend walks 3 kilometers an hour east. We will calculate the relative velocity vector. That's of my friend relative to me. So let's start with a diagram. My journey can be represented with this vector here, 2j. J because it points directly vertical, and 2 because I'm going at 2 kilometers per hour. Similarly, my friend's journey will be represented by 3I, 3 kilometers an hour in an easterly direction. Now, the relative velocity vector is going to be my friend's minus mine. So when we're doing such problems, whichever one is second, that's the vector you subtract. So the relative velocity vector here will be friends minus mine. It'll be 3i minus 2j. So that's going to be a vector down here. So if I let that vector be r, the magnitude of r, we can easily calculate. It's just the square root of 3 squared plus 2 squared. So that's the square root of 13, which is about 3.61, and the units are kilometers per hour. So this means that if we keep up these constant speeds, each hour, my friend and I will move further apart by 3.6 kilometers. Now, this here is the relative velocity vector. You can see that it points in a southeast direction. So what does that mean? It means from my perspective, almost as if I were to stay still, my friend appears to be moving southeast. Another way to look at that is as we keep moving, my friend is moving further and further to the southeast of where I will be. Again, because it's relative to me, it means it's done from my perspective. All right, let's now look at another question. I drive on a bearing of 200 degrees at 80 kilometers an hour, calculate my average velocity vector. So it gets a bit tricky with bearings because remember, they don't follow the same pattern of angles as does the unit circle. So bearings actually start here at 0, then they go 90, 180, 270, and then we get back up to 360, which is the same as a 0-degree bearing. Of course, for the unit circle and the way that we represent the direction of vectors, we have 0 here, 90, 180, 270, 360. So bearings go clockwise, whereas our normal angle goes anti-clockwise. So our first goal here is if I'm going down here at 200 degrees bearing, what I have to do is convert that into the normal angle that we use for direction. So the normal angle we use for direction is positive x-axis going in an anti-clockwise direction. So for a 200-degree bearing, this angle in here will be 70. So the direction of the vector is 180 plus 70, which is 250. So in polar coordinates, the vector will be 80, which is the magnitude, because I'm going 80 kilometers per hour, 250 degrees. So converting that back to Cartesian coordinates, remember the x component is 80 cos of the angle, and the y component is 80 sine of the angle. So putting those numbers on our calculator, we get about 27.36 I minus 75.18 J. So because I is the unit vector that points due north and j the unit vector that points due east, these negatives just reverse the direction. So we can interpret this as saying if I travel 80 kilometers an hour on this bearing, so I'm traveling at a constant speed, each hour I'm moving 27.36 kilometers to the west and 75.18 kilometers to the south. All right, let's now look at a harder problem. So here we have a drone that kind of wishes to move north at 10 meters per second, but there's an easterly crosswind of 5 meters per second. So what will happen is it will have a computer on board that will cause it to recalibrate its movements, because the wind will prevent it from going due north. Now in this question, we're going to calculate the direction and velocity of that recalibration. In other words, what must the computer tell the drone to do in order that it does move north at 10 meters per second. So let's again start with a diagram. This is how the drone wants to move, or we want the drone to move. We want it to move 10 meters per second in this direction. So this will be represented by the vector 10j. Now, an easterly crosswind means it's blowing towards the east. So this will be represented with the vector 5i. Of course, to add vectors, they need to be head to tail. So we will move that vector over here. The starting point doesn't matter. So under these conditions, the drone will move according to the sum of these vectors. It will actually take this path here, and this will be the vector 5i plus 10j. So you can see that it's not moving due north. We want to recalibrate it so it is moving in this direction. So firstly, let's let this vector be v and let's calculate its magnitude. See, the drone can't just fly at 10 meters per second. It needs to go a little faster to overcome the effect of this wind. So how fast does it need to travel? Well, we just calculate the magnitude. It's the square root of 5 squared plus 10 squared, root 125. It's approximately 11.18 meters per second. So that's how fast the drone will need to travel. But of course, we also need to change the direction in which the drone is traveling. If it aims in this direction, it ends up going over here. So let's calculate the direction of this vector v. Remember, it's always the angle made with the positive x-axis going in an anti-clockwise direction. We can easily calculate theta. It's always tan inverse of b over a, where b is the j component and a is the I component. So if we put that in our calculator, we get about 63.4 degrees. So that tells us that under these conditions, as stipulated in the question, the drone would travel in the direction 63.4 degrees. So the computer is going to have to tell it to recalibrate. It's going to need to tell it to move according to a vector that is equal and opposite. So because it's being pushed, this is like 63.4 degrees north of east, we're going to need to aim at 63.4 degrees north of west. But of course, we don't call this direction 63.4 degrees. What we want is the angle made with the positive x-axis going in an anti-clockwise direction. We want this angle here. So that angle will be 180 minus 63.4, so it will be 116.6 degrees. So what the computer will need to tell it to do, it will need to tell it to move according to the vector, I'll call it W, 11.18, that's the magnitude, that's the speed at which it must travel, and it must travel an angle of 116.6 degrees. So this is the magnitude and direction in which the drone must travel, so that when the crosswind blows it, it is going due north and it is moving 10 meters per second in this direction. Of course, I've given W in polar coordinates, but you could easily calculate this in Cartesian coordinates as well. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.